All right, so now that we're talking about multivariable functions, we'll go ahead and need to expand out into the idea of limits and continuity, much like we did in Calc 1. In fact, that's kind of where I want to start. I want to recall R2. And so in Calc 1, and you started studying limits, one of the first pictures you probably saw was something that looked like this, where y equaled f of x. Maybe we'll put an a here, and we'll say that the limit as x approaches a of the function equals L. And what that means is we're approaching a, coming in from both directions, to a value up here, which we called limit L. All right, now, we also know that this limit exists if and only if the limit as x approaches a from the right and the limit as x approaches a from the left also equal L. Okay, so notice if you approach a from the left, if you approach it from the right, you need to get the same thing, and if you do, the overall limit is L. Now, let's take it into Calc 3. So let's consider R3. So if I construct the XYZ space and I put some surface in here, and if I'm interested in now studying the limit as we approach something, let's say we approach this point, the problem is we've got infinitely many ways now to approach that point. Earlier, you can see along this curve, you can only approach it this way, you can only approach it this way. But since now we're in a higher dimension, you could approach this point this way, this way, this way, infinitely many ways. So for us to be able to say that the limit as xy approaches AB of f of xy equaling L, we have to be sure that every single path approaching this point gives us that same limit. And sometimes that's a tall task, but we'll take a look at some examples and better understand what's going on. Now back to the notation here briefly. This is in fact the limit as xy approaches AB, so all the xy ordered pairs approach the ordered pair AB of the function equals the L. That L will be the z value, much like the L was the y value up here. All right, so before we take a look at those examples, the book has, looks like 7 properties that they've laid out in your textbook on page 802. I think it's important to take a look at those. None of them will surprise you. They're all things that you would have learned in Calc 1, but because of the nature of this having multiple variables, sometimes working with it is a little bit surprising maybe. So we'll take a look at some examples, but please make sure you take a look at page 802. The other thing that you won't see on page 802 is a mention of L'Hopital's rule. L'Hopital's rule only works for single variable functions. And so if you have a multivariable function and you want to use it, then you're going to have to reduce it down to a single variable. Again, something that I will mention in an example. But do keep in mind the properties that you see on page 802 are legal, and L'Hopital's rule for multivariable functions is not. All right, so I've gone ahead and put the first example up on the screen. We've got the limit as xy ordered pairs approach the ordered pair 1/2 pi of this function right here. Now, first things first, when you're told to investigate a limit, the first thing you did in Calc 1 is the first thing you're going to do in Calc 3. You're going to plug it in. So I'm going to plug in my 1/2 for x, and I'm going to plug in the pi for y. And if I do this, I end up with a 1/2 pi squared sine of pi over 2, which is a real number. Therefore, we are going to have a limit by simply plugging it in. And so when you simplify this down, you get a pi squared over 2 for your final answer. So even though some of them are much more complicated, don't ever forget, start by plugging in the point. All right, so for the second example, we'll start off by plugging in the 0, 0 in for x and y. So I'll have a 0 over 0, it looks like, when I plug all that stuff in. So unfortunately, it didn't work in this example, but we can still manipulate this much like we would have in Calc 1. So if you looked over those properties on page 802, one of the things that you'll see is that you can go ahead and separate this somewhat. And what I mean by that is I'm going to keep my y's and my x's apart. Now, I know that my y value is approaching 0. So if my y value is approaching 0, that whole piece right there just goes off to a 1. And I know that my x value is approaching 0, so this whole thing here, remember this is a Calc 1 limit now, this whole limit right here also goes off to 1. So by separating it, we can see that the result is just going to be 1, even though when you take both of these and plug them in directly, you do in fact get the 0 over 0. All right, so taking a look at this next example, just pay close attention to the notation. It's really not anything different, but it looks like a lot. It's the limit as xy approaches 2, -4. Here's our function. And then underneath it down here, this is pretty common. If there are going to be any restrictions, they'll place them down here, things just to look out for. And so you'll see that on a few of these problems, but for the most part, it's more just a formality than anything. All right, so as we take a look now at what we have, first things first, if you take the 2, -4 and plug it in, you can trust me on this one, you will get a 0 over 0. And so what we'll do is we'll just go ahead and use a little bit of algebra and factor. So I'll carry the limit notation down. And then the y plus 4 on top will stay put. And then we can first off start by factoring out an x. So if I factor out an x, that's going to give me an xy minus y, and then a plus 4x minus 4. And then it looks like I can factor the rest by grouping. So if I group like this, we'll have our x still out there. I'll take an y out of there and get an x minus 1. I'll take a 4 out of there and get an x minus 1. So it looks like the whole thing factors then into an x, a y plus 4, and an x minus 1. All right, so just like in Calc 1, it's not surprising that something there goes away. And here we've got now a 1 over x times x minus 1. And since you have gotten rid of the y variable, if you chose to write it like this, that would be fine. If you chose to now write it as x approaches 2, since there is only an x, that's fine as well. It's entirely up to you. So when we evaluate, we get a 1/2. So last couple examples, as you saw, there's really nothing new in terms of limits that you haven't done before. We're just introducing this additional variable that is always compensated for in what we're asking. All right, so for the next example here, we've got our limit as xy approaches 0, 0, 1 minus cosine xy over xy. If you take the 0, 0 and you plug it in, you do get in fact, a 0 over 0. And so we need to figure out something else to do. And in this particular case, I made mention of it earlier, we're going to go ahead and change from a multivariable limit to a single variable limit. If I let xy equal u, all right, if xy equals u, then my limit is going to look something like this. I'm going to have 1 minus cosine of u over u. But I don't have any x's and y's anymore, so I don't want the limit notation to say x's and y's. But we know x and y both are going to 0. So if x and y are both going to 0, then the u also has to go to 0. So now my notation would look like this. Knowing again, once you reevaluate, you're still going to get the 0 over 0 for the whole thing, but being a single variable limit, now we can use L'Hopital's rule. And so the limit as u approaches 0, this would be a 0 when I take the derivative of it. This whole thing here would come out to be sine of u over 1. And when we evaluate now, the u going in there, sine of 0 is 0, we end up with 0 as our final answer. And so this type of substitution is not very uncommon. In fact, it's one of those things that hopefully you'll feel more comfortable with using more often than not. But it's a wonderful trick to get down from multivariables down to a single variable, which you've been studying the past 2 courses.